In this video, we're continuing on with the second half of a look at network models. So now we're going to explain the major functions of the network software with the OSI's 7-layer model. So we're looking beyond the wire to layers 3 through 7. In the previous video, I talked about how we have our MAC addressing that lets us communicate between devices on a local network. However, if we need to communicate to devices on another network, we have to have a delivery system. So we have our hierarchical addressing system, our IP system. And this diagram, Myers shows us a magic box in the middle that is required in order to deliver content from one network to another. And that magic box would be a router that routes IP addressing. So how does data get from one system to another in large networks? We have a logical addressing method. It's hardware independent, does not matter what kind of hardware you're using. So TCP/IP is a suite of network protocols. And a protocol is a set of communication rules. So IP is our network protocol. It creates rules for how to get packets from one subnet to another and provides unique identifiers for each system. So packets are created and addressed at layer 3. The Internet Protocol, or IP, is our primary logical addressing for TCP/IP. We started our network in the 90s with multiple logical addressing. We had Unix had IP, Novell had IPX, and Apple had AppleTalk, Digital had DECnet. So there were contenders for our logical addressing. However, because Unix had so well developed their IP functions, that more or less won the market. So even now we continue to make ground with TCP/IP being the language for networking. We'll get later on into one of our latter chapters. We were talking about industrial systems, and there was an industrial protocol that has been long in place that is now being replaced by TCP/IP and allowing everything to just communicate on the network on the same logical addressing. So a logical address, an IP address, is a unique identifier. It is a 8-bit number. It's 4 8-bit numbers ranging from 0 to 255, separated by periods. So you saw that when we did our binary conversion. Now we set things up in groups of 8 bits, and the values could not be more than 255, and they were separated by periods. So we have our physical addressing, that is the MAC address from the NIC. This is a small router, just demonstrating that we have to have a layer 3 device that can route or direct the traffic for IP addressing. But when you get into the Cisco courses, you'll see much more complex routers that are the enterprise level routers. All right, so playing on layer 3, the network layer, every device has to have a MAC address and an IP address in order to communicate. Even on a local network, IP addressing is expected. This is a simplified diagram of a IP header. There are actually many more fields that we'll look at later, but we have our source and destination IP addressing that's attached to the data, and it creates the IP packet. So the packet is actually the payload within a frame. So when we talk about passing that packet down the stack to the layer 3, then the layer 3 will add the frame header and the frame checks in the frame trailer, the frame check sequence, and turn that IP packet into a frame. But that payload inside, when we call it the data field of the frame, that's actually the packet. Data is sent from one computer to another on a TCP/IP network, and it can go through many routers. So each router is going to strip off the incoming frame, read the IP addressing, direct the packet to the exit interface that is the right one for the destination network, create a new frame needed for the connection to the next router. So this illustrates that process. We have a frame coming in, and that frame has a header and a trailer, and this would be the packet header and trail, and then the data. And the router is going to take off the header and the trailer of the frame so that it can read the IP addressing of the packet. And then it will direct it to the appropriate interface to go outbound to the device it's going to. On the way out, it will get a new header and trailer for the frame to be sent to the next device. And when it does that, the MAC address actually changes, because the source MAC at that point will be the router, and the destination MAC will be the next hop device. So at the layer 4, the next layer up the model, up the stack, most data is much larger than a single packet. So this is a little confusing, because on one hand, we're talking about going physical, and the physical data link, and then the network layer, and now the transport layer. However, the reality is that data starts with the application layer, comes down to the presentation and session, and then the transport. So we have this data coming down. It's much larger than a single packet. And at the transport layer, that data is going to be broken up into segments. So the transport protocol breaks up the data into chunks called segments. There are two different protocols. We have TCP and we have UDP. UDP are officially designated as datagrams. However, in most contexts, we just refer to both as segments. So the transport protocol gives each segment port numbers for our TCP segments, and a sequence number also. So both UDP and TCP get port numbers. Now, port numbers are identifiers for applications. So what happens from those port numbers is that there is the connection made from application to application on the send and receive devices. All right, so it's going to hand segments then to layer 3 for encapsulation into packets. So we've got that data coming up from the application layer, and then it gets broken into segments. It gets handed to the layer 3, the network layer, to be packaged into a packet, and then it gets handed to the layer 2, the data link layer, to be packaged into a frame, and then that gets translated into bits onto the medium. All right, so back to TCP. The TCP sequence numbers notify the receiving system of the total number of segments and how to put them together. So it would be similar to the boxing of numbers by UPS. And you see down here on the label, it's box 6 of 50. So if someone were receiving 50 boxes, they would wait until they got them all in and numbered and make sure they had everything before they passed them along. Okay, so the function of the transport layer is primarily the segmentation and then the reassembly of the software. So the text says that it initializes requests for packets that were not received. And I want to clarify that it's not really the recipient that requests packets that were not received. Really, TCP sends acknowledgments for segments received, and segments not acknowledged are resent by the source. So it's just like when you're in a conversation with a friend and you say something and the friend doesn't acknowledge, you assume they weren't tuned into what you were saying, but they didn't receive it. They didn't give you an acknowledgement. So what do? You say it again, right? Well, that's the same thing. That's exactly what happens with TCP. If it's not acknowledged, it's resent. So back to our OSI model. At layer 3, we had routing, which involves our path selection, because the IP will be directed to the destination network interface of the router. All right, and then at layer 4, the word associated with layer 4 is reliability. And that's really because of the reliability afforded by TCP with the acknowledgement and sequencing of the data. So TCP is connection oriented, while UDP is connectionless communication. Connection oriented protocols require connection between the client and server before communication can start. Now, in this chapter, we don't talk about, I think in a subsequent chapter, we'll talk about the actual TCP handshake that happens, but there is a complex setup that lets the two devices make a connection prior to sending data. So that connection is established, it's a virtual circuit established before data is sent. All right, on the other hand, UDP is a connectionless protocol that just starts communicating without first verifying a connection exists. But they both have their purposes because when things need to be, when every piece is essential for the communication, we want that connection oriented. However, when data must be sent quickly in order to be valid, then UDP is better because that acknowledgement process takes time. Acknowledgement reassembly takes time. So TCP receives application layer data, breaks the application data into chunks, adds port numbers and sequence numbers, creates a TCP segment, and then it hands this TCP segment to the network layer, which creates the IP packet. So segments are the payload within the packets, just like packets are the payload within the frames. TCP segment remains after stripping away all the IP addressing from an IP packet. The TCP segment port numbers are going to be numbers between 1 and 65,536. A logical value assigned to a specific application or services. So a web server listens for or looks for TCP segments with the destination port numbers 80 or 443. This is HTTP and this is HTTPS. This diagram just demonstrates how much more complex a TCP header is than a UDP header. So a TCP header has the source and destination ports, has a sequence field, has an acknowledgement number field, and then a bunch more, as Myers puts it. But that also includes a checksum, and then it has the data. The UDP just has a source and destination port, a length field, the checksum, and then the data. So it's much less overhead. So while TCP has the complex handshake, UDP just says, here it comes, hope you're ready. All right, so UDP datagram created at the transport layer includes port numbers and link numbers plus a checksum. Now they both do have a checksum, and then it combines the header with the data. UDP datagram lacks most of the extra fields found in TCP segments, and it doesn't care if the receiving computer gets the data. It leaves that to the application to deal with. Now, going on to the next layer, layer 5, the session layer, we talk the very least about the session layer. It is almost like services running in the background. When you go to Task Manager and look at the services that you never see, and sometimes you can't even tell what they go to. Well, that's the same thing with the session layer. It's the one we know the least about. So one system may be talking to another system simultaneously. So Myers says the session software handles the process of connecting applications to applications. And I contend with that because I have 20 years of experience with Cisco, and the application connection is made by port numbers, and that port numbers happen at the transport layer. So the session layer is more like the traffic cop. It handles all the sessions, initiates sessions, accepts incoming sessions, and opens and closes existing sessions. So here we have a scenario where we have two different computers that need to access Janelle's system. So Janelle's system connects to the printer. It's the connection to the printer. Computer A needs to access Janelle's Word document. Computer B needs to access the printer. So if suppose the conversation from the Word file came in first, that would get the first opportunity. However, if it's taking a long time, the session layer may say, hold on, let me let this request to the printer go through. And then when it's finished, let the conversation with the document continue. So it's more or less the traffic cop. All right, so at the session layer, we have the dialogue. We have session tracking and naming. So it's that opening and closing of conversations. Then moving up to the presentation layer, the presentation layer translates data from lower layers into a format usable by the application layer and vice versa. So that's where encryption and decryption happen, compression and decompression, translation from bits into file formats, meaning like MPEG and MP4 and all of that, and from file formats back to bits. So we have our data conversion in by Meyer's terms. I call it the translation layer. And then layer 7, the very top layer, allows users to exchange data on a network. Now, we're not talking about, when we say application, we automatically think about our software applications like Microsoft Office and, whatever programs you tend to use. But this is not what we're speaking of. It's the web browsers. It's the user interface. So whatever allows the user to actually interface with the network, that is the application layer. But all operating systems also have application programming interfaces at the application layer for network aware applications. So there is some communication that goes on that we never see. It's in the programming level. So if you're one of those who are coming from the computer science field, you may be very be very aware of APIs. But so APIs are another part of the application layer. Applications may include additional functions like encryption and user authentication and tools to control the look of the data. So where in wireless, we're going to have a little bit different functionality because we have the authentication happening at layer 2. In other applications that are running on the cable networks, the authentication often happens at layer 7. So here we are with layer 7 added to the top of the stack, and it is the user interface and the APIs. So that whole process of going from the initial data from a user to down the stack to the cable is called encapsulation. It's the entire process of preparing data to go onto a network. So all the steps from application, presentation, session, transport, network, data link, and physical layers. And then when it's received on the other end, the data has to go through the decapsulation process, the reverse process of the encapsulation, stripping away all the extra header information as the data goes up the stack and eventually becomes the application data received by the destination host. So one last thing, and that is that we have terminology that we use to describe our data at each layer. And we call these the protocol data units. So from application layer, presentation layer, and session layer, it's all still called data. When we get to our transport layer, our data is referred to as segments, and see, this is where I'm saying here we don't distinguish between segments and datagrams. They're all just referred to as segments. And then at layer 3, we have packets. At layer 2, we have frames. And then as it's transferred onto the medium, it is referred to as bits. So we have explained the major functions of network software with the OSI 7-layer model for layers 3 through 7.